Okay, so for the path integral formalism, what have we done? Okay, and what are we going to do today? So we started from the propagator. And by propagator, I mean here the matrix element of the time evolution operator in the position representation. Okay, and from that we got path integral representation. Okay, and we did that for one state system. Okay, it was with 1p, 1q, and one harmonic oscillator. And it was for a bosonic harmonic oscillator. Okay, so it could be used to describe some bosonic degrees of freedom. And so this is, and so okay, so this was the first step, and in fact it's what we're going to do today, but in the context of if we have now fermionic degrees of freedom, how can we deal with that? But then, so on this part, we also look at the semi-classical approximation, and then we use this calculation to, in fact, compute exactly the propagator for harmonic oscillator, and this indeed can also be used, in fact, to compute any the path integral for any quadratic action. Okay, so this can be generalized to any quadratic action. And then we look at perturbation theory, where here the point is we don't have anymore just a quadratic action. We have an action with a term beyond quadratic. And so we don't know how to write a path integral representation exactly for this kind of action. So we need to go to the perturbation theory. Okay, and then we use this trick of acting with some function. We add a source to something, to an action we know to compute, and then we act with some differential derivative. Okay, so this, and yesterday what we did was to define now the notion of correlation function. And the notion of functional generatrice, okay? And so here, the two approaches can be seen, at least the trick we used here is more or less the same that we are using here to compute correlation function, except that here, what you want to compute is something like this, an expectation value, so usually between vacuum, where then you have some okay, so now we know how to write this kind of object as a path integral, and it's going to give you a kind of something quite similar to what we use, except that now we have function here, x of t, a product of function. Okay, and so now the issue contrary to here, so here the issue was more than S was something quadratic plus something beyond quadratic. And so the perturbation for this part, so here this action has to be something that we know how to compute, and then we use the kind of same trick acting with functional derivative to introduce this function here. Okay, so the idea is always how can I go back to something I can compute, and the only thing you can compute right now is the path integral for a Gaussian action. Okay, so meaning a quadratic one. Okay, so we don't know how to do many things. All the other things that you can do is kind of perturbatively. okay? Or using a trick going back to this, to what we know. Okay, so what are the limitations here? As I said, what we did was for a one-state system and for bosonic system. Okay, so there are, of course, and there are other limitations, but these are two limitations that I just want to point out. Because so what we are going to do today is still work on a one-state system, but go to a fermionic degrees of freedom and see what if we can do this first step here. Okay. But of course, it will be also interesting to work with many state system. And for this, so what you need to have as a background is to at least one way to deal with that before going to the path integral formalism is to use the second quantization formalism, and this is what you're going to see tomorrow. Okay, so tomorrow you're going to deal with something a bit more complicated than a one-state system, but still bosonic. And today we still stay with a one-state system, but we go to fermionic. Okay, so this is the idea. So, so here you see that to do the first step, we're starting from more or less the first part of the course were about canonical quantization. And in the canonical quantization, remember, so we are dealing with operator. And they don't commute. And then when we go to the path integral, okay, all the objects you are dealing with are classical. So you have classical functions. So at the end, in fact, if we go back, so to introduce this formalism, if you remember, we started from classical mechanics, and we were trying to find arguments why we need to get rid of the fact that these operators are commuting and etc. But then when you write everything in the path integral formalism, in fact, you're back to numbered value function. Okay, so then you're back to this kind of object which are commuting. Okay. So now if we want to go to work with particles that are called fermions, then we are going to work with operator that satisfy anti-commuting relation. So I'm going to introduce them. So I guess maybe you're already a bit familiar with fermion, and you're going to have a lecture on statistical mechanics, so maybe you will talk a bit more. So there are particles that just obey some Fermi-Dirac statistics, and something which is quite important is this Pauli principle, saying that a state can be either empty or occupied once. And because of all this property, we are going to see that it's very useful to work with what we call Grassmann number, at least at the classical description. Okay, so here, these are still operator, but then, so when we arrive here, if you look at now this kind of function, then this become commuting. And now if we want to go to define the kind of classical equivalent of this operator, we are going to introduce the notion of Grassmann number. And these Grassmann number are going to be anti-commuting number. So we're going to go to something like this, okay, in the framework of the fermionic degrees of freedom. And this is what we're going to call so I'm going to do checking your homework one. I've seen that not everyone is familiar with Grassmann number, but I don't want to spend too much time on that. But I think, anyway, it's still useful to refresh things about Grassmann number to get used to do some short calculation with them. So we're going to do a short review. So everyone has this. Okay, so I printed that because like this you don't have to write everything, and I don't have to write everything either. And also what I want you to do, so we're going to go through together, and of course there's some blank part left. So we're going to do this small computation together, and I want you rather to focus on doing that rather than to writing all the details. Okay, so this is the first part on for today. It's going to be and the tutorial this afternoon is going to be working with this kind of object and as the Hamiltonian for a fermionic harmonic oscillator. Okay. Okay, so the first paragraph that you have is just more or less the definition where we introduce n generator satisfying anti-commutation relation. So I'm not going to enter into the mathematical detail of the Grassmann algebra and etc. We're just going to more or less use this to try to do some, to derive how to differentiate when you're dealing with Grassmann number, how to integrate, what does it mean, is there an equivalent of integration, and what we used also here, we said that the only kind of path integral we know to do is when you have a Gaussian integral. So can we define a notion of Gaussian integral too? And then, of course, so yeah, we need the notion of derivatives, the notion of integration. Okay? So these are the main part. So maybe check just before going on. So I think most of the questions, so you had 3 questions to answer that are at the top of your sheet for the homework 1. So I think question A was fine and B was fine for everyone almost. But so just question C. So I'm telling you that a function of Grassmann number is defined as a Taylor expansion of the function. So if now we consider the case n equal 1, I was asking you how you can expand that. And I've seen that not everyone figure out the why, in fact, it's going to calculations are going to be, in fact, so easy with Grassmann number. It's just because using Grassmann number is, in fact, a way to linearize, okay, everything. Because here, this is exactly equal to that. Is that clear to everyone? That from the anti-commutation relation, you have that theta square is equal to 0. Okay, that's the Grassmann number. Okay, so then just few remarks. So yeah. Contrary to a real number now or complex number, the generator of the theta k, they don't have any magnitude. And so you cannot consider a kind of order set of Grassmann number, okay? And so do you know what, there is only one number which can be, which at the same time is a complex number and a Grassmann number. So it's 0, okay? Any other thing are completely different. So let's go to differentiation, okay? Because it's the first thing we're going to use. And doing some manipulation, hopefully you're going to become familiar with that to follow the calculation I'm going to do to define the path integral. Okay, so we define the differential operator as acting on the left of a function. So if we just consider this kind of operation, this just tells you that it's delta ij, okay? And this operator, so another point is that this anti-commute with the other delta j. So from that, from these two assumptions, let's write together what is going to be the Leibniz rule in the case of differentiation in terms of Grassmann number. Okay, so this is at the top of page 2. You have some a blank part to fill up. So let's just consider the derivation with respect to. So I'm at the top of page 2 for you guys. Okay, so let's start. So first, I'm going to act on the first one, okay? And I'm just using this rule. It's going to give me a delta ij. Oh, sorry. And then to get to the other term, I have to permute here, okay? So because we have this anti-commutation here, what do I get here? Yeah, so then I get minus okay? And so you have to be careful of this minus and really remember this. This is really what makes the things different from what you're used to. Okay, so since we have differentiation, let's see what we can say about integration. And so the point, so I'm not giving you any justification why it is like this, okay? It's some kind of compatibility relation between the fact that what you want to have when you say that you differentiate and then integrate. Okay, so integration here is more seen as definite integral, okay? But so what is really important is that integration with respect to a Grassmann variable is really equivalent to differentiation. So what do I mean here is that if now, so I'm considering just one variable for the moment, and then we're going to generalize that to many variables. This okay, so this is by definition. So what this is going to imply, so let's do some very simple case together. So this is at the equation 4 for you that you can complete. So if here, what do I get? Yeah, okay. It's the derivation of 1 with respect to theta, so it gives 0. And then if now I'm just doing the next simplest integral, yeah, okay, so here it's 1 because and so of course we can generalize this expression to the case of many variables. So I'm going to write it just because I really want you to, so you have it already written. Of course, the order here is important, okay? So we keep the same order the way we write, okay? But this means that we're going to act in the, meaning that we're going to start with, so let me write this. So this is on, okay, meaning that you're going to start with the derivation with respect to this variable, theta n. Be careful with the order here. Okay, so now that we have notion of differentiation and integration, you know that usually it's what you use when you want to do some change of variable, okay? So let's see if we can look at the change of variable. So any question here? Is it, yeah.
Should we just take that integration equals differentiation as like a definition of integration?
Yeah, so this is like on one variable and on many variables. This is the definition. Of course, as I said, if you want to, we could go to kind of one step of abstraction or higher and try to find what are the rules. Once we have the differentiation, we want some kind of compatibility relation between differentiation and integration. So what are the rules that we want to preserve, and then kind of derive this. But I don't want to go to this stage. So here we take that as a definition, and it, yeah, in many, at least if you're just interested in calculus of Grassmann number, then this is usually the way we deal with, we introduce the integration. Okay. Okay, so let's look at the change of variable. So if now, so in the case n is equal to 1, so for you it's going to be equation 6. we want to consider this change of variable. So we look at the integration. And by definition, this is, and now if we change variable, so A here is just a complex variable, complex number, okay? So it's not a Grassmannian. So here I want to write this in terms of theta prime. So it's going to be and so what do we get? We just get that this is equal to A times okay, so you see that here the change of variable that you for the measure, your measure term is the other way around that the one you used to. And if you extend that to many variable, what you get is that the determinant of your transformation is going to appear, but instead of with the inverse is going to be really the determinant. Okay, so I let you just read this. Okay, so one important function for us is going to be the delta function. Okay, so let's see what we can say about this function. So we're going to define it the way we want. Of course, I haven't used the right table. So let's go here. Okay, so let's move to delta function. And so let's first, again, look at the case with one variable, and then we can generate things. So we want to look at this kind of equation, and we expect, of course, if it's a delta function, that as a result, we get f of alpha here. So this is for a single variable. So for a single variable, so this is at the top of page 3. Generally, how can you write f of theta if it's if you have only one theta variable? What is going to be the general form?
F0 plus a linear term.
Plus okay. So let's apply this to this explicit form now and try to deduce what is going to be the delta. Okay, so here, and for that you need to remember some property of. So at the end, what you expect, okay, you want that here you get f0 plus f1 of alpha. We're here, so f0, f1 are complex number, okay? So if you get a f0, this means that acting with the derivative, okay, so it's a derivative. So this means that the delta should put a theta here, okay? So you should have something like, so let's try to guess what is the expression of that. Or maybe someone already found? Yeah.
Sorry, is this f1 of alpha or?
No, times, so it's f of alpha.
Oh, I see.
F can be written this way, okay? So now I'm just replacing what is, so this is the value of f of alpha, where we just know that this function can be always expanded over the generator. So here, when n is equal to 1, we only have one generator. So this is the general form of a function. Okay, so anyone got the solution here? Theta, you're saying plus alpha. Okay, so let's check for the, so let's try. Okay, so now if we have theta plus alpha, So let's do the product and the differentiation. So here we're going to get theta f0 plus then the theta with f1 theta is going to be 0 because theta squared is 0, okay? And then I have plus, so some f0 alpha plus f1 alpha theta.
Because of, yeah.
Okay, so now we want, okay, let's see if everyone agree with that. So it's going to be a minus. Let me put some color. So here it's a minus because, so you see now we integrate, so it means we differentiate with respect to theta. So here it's going to give us the f0, that's fine. That this is a constant with respect to theta, so it's 0. And here we want to differentiate with respect to theta, but we have this alpha there. So this means that we need to cross, okay? So it's a minus is coming out, so we need a minus here. So we need a minus to get this solution. Okay, so the solution here, no one get confused, is so this was to complete an equation 10 for you. And then you can, of course, expand this result when you have n variable. But again, now we have to be careful with the order, okay? So I'm not going to prove it explicitly, but just each time you have to expand something in terms of Grassmann number, be careful with the. So this was for equation 11. Okay, any question here? Yeah.
Is this the function of Grassmann numbers then odd or even? Or how does parity work here?
No, it's only, there is only one, so it's like, but so if, so, yeah. So here it's because, so this is also a Grassmann number, so they're anti-commuting. Okay.
Oh, okay.
So we started, of course, with just one, but we need to, okay, because here this is, your function is a function on a Grassmann number, so this is another. Okay, so then, yeah, then I'm introducing the Gaussian integral, but so with what we are going to do, of course, if we were then really going to go into detail on the path integral formalism for fermionic system, then we would be interested in Gaussian integral because it's very similar to what we have done for both systems. The one we're going to be able to compute are going to be when it's written in terms of Gaussian integral. But I can just explain you more or less the step if you want to try to prove this expression. So here, if we consider this integration, of an exponential, so theta one can read. Okay, so it just rewrite, if it's too small, exponential of so this way. So the way you can prove the result, so at the end you're going to get that this is the determinant of your matrix. So we're here, since all these variables theta I star and theta j are non-commuting, okay? Then this means, of course, that you want that this is antisymmetric, okay? Otherwise, it's going to, this term is going to be 0. And so to solve that, you can just perform a change of variable where you're going to plug and get to the result, okay? Okay, so this was to define what is a Gaussian integral. Sorry.
What does a star mean here?
So it's going. Yeah. So I haven't introduced the notion of complex conjugate, but in fact, it's just here you can see them as just independent, just all being part of the same Grassmann algebra, meaning they all anti-commute. Okay. But then we're going to see that when we have a even a Grassmann algebra of even side, then you can always say that you divide more or less your algebra into two parts, and then we're going to introduce this notion of complex conjugate where we add some relation between them. Okay, so I'm going to come to that in a moment. So let's first, since you're following, you have the paper, let's follow maybe. Then the next part is the functional derivative and then the complex conjugation. So of course, so we are not going to use so much functional derivatives today, but I just want to rewrite the definition just because, again, it's allowed to make few comments about the difference with when you're dealing with Grassmann number. So here we're dealing with the Grassmann variable, and S and T are just some complex parameter, okay? And we define this as okay. So it's almost the expression is very similar to the one you would have in with just complex number, okay, and functional. So epsilon here is a Grassmann number. So can you see why? So what is the difference? The main difference that you have between this formula and the formula you have with the functional derivative that you know? Yeah, there is no limit. Okay, and you see why we don't need to take the limit here? Okay, so our function is defined. I told you it's defined by its Taylor expansion. Okay, and now if we do the Taylor expansion with respect to this epsilon, which is a Grassmann number, it's going to be exactly linear, okay? Because epsilon squared is going to be to 0, so we don't need to take the limit here. And another important point I just wanted to emphasize on this formula is that, in fact, the division with respect to the Grassmann number is not well defined. So here it's fine because we have something which is proportional to epsilon. Okay, so what does it mean? That just means that you pick the number which is in front of epsilon when we write that there is this derivation. But in general, the derivation with the Grassmann number is not well defined. Okay, so this is for the functional derivative. Any question? Yeah.
So could we have also written epsilon times t minus s? Is that the same?
No, but here it's a real number. It's a delta on complex variable.
That thing in orange is only if the argument is a Grassmann.
Yeah. Okay. Yeah. This is a delta defined on Grassmann function. Here you see that, yeah, this is a Grassmann field, okay? And here it's a Grassmann number, so here it's just real, the real part. Yeah, thanks. Okay, so the last point is about so if now we consider two sets of Grassmann number, okay, we can define the conjugate, the complex conjugate of theta e. So as giving the other number. But they are all anti-commuting, okay? And so we define what is important is this relation that you have here. So if you take the product of two Grassmann number and you take the complex conjugate, then it's going to change the order, okay? And you want this because then you will see, so using this property, so this is the last, at the end of your last page to complete. If now you look at the complex conjugate of this product, what do you get here? Yeah, the same, okay? So it's a kind of reality condition. Of course, you cannot say that it's a real number because, for example, if you act with a derivative on this, yeah, it's not going to, or if you multiply just this number by theta I, it's going to vanish. So it's not really a real number, but it's just you have this reality condition, okay, which is nice. Okay.
I have a question.
Yeah.
How do I know that theta I star of a star is theta I?
So how do you know? Ah, yeah, I didn't. Yeah, it's also part of. Yeah. So your point is that. Yeah, and then. I guess you need to add it in the kind of definition in the relation. Yeah, thanks. You need to add. Also, you can, yeah, it's the same for this notion of complex conjugate. If you work at the level of the algebra, you can define that in a bit more mathematical way, introducing really the kind of Hermitian thing. But yeah, I just want to give you the result here. Okay, yeah.
For these theta I and theta I star, those are independent sets.
Yeah, so a bit the idea is, well, if you start from a Grassmann algebra with a even dimension, meaning that you have like 2n, then the idea is a bit that you can always consider two sets that of this. So they are all anti-commuting, and then you to deflect the complex conjugate, more or less, you impose this kind of relation between these two. This kind of.
Okay, so theta I anti-commutes with theta I star.
Theta I and
theta I star anti-commute.
Yeah.
Okay.
Yeah, we're going to use it in very soon. Yeah. Okay. So any question? So was that okay as a reminder, or if it was new, was it fine to follow? Or? Okay. So we're going to try to use some of these tools. Okay. We're going to start with operators at the quantum level. Okay. We look at the Hamiltonian. And as we did before introducing the path integral, we did kind of a canonical approach for bosonic particles. So we're going to do the same here very quickly for just the fermionic degrees of freedom. And then we're going to introduce the path integral. Okay, so this is the second part. And it's working with an Hamiltonian. So here we're not going to have right now Grassmann number. We're going to see that we're going to introduce them, in fact, when we want to define some coherent state, and coherent state are usually. And the example we're going to take, because we're not going to do that in general, is fermionic harmonic oscillator. So the Hamiltonian we're going to start with is where here this operator satisfies this following condition. So write the anti-commutator of C dagger is equal to 1, and then and so in fact we can, so first let's introduce, so this is our Hamiltonian. Now let's introduce the number operator, just because and if you look at this, you can really rewrite this equation in terms of n, and it's just going to be n omega minus 1/2, okay? If you just use the commutation relation here. Okay, so you will, in the tutorial, you're going to show that this operator has only 2 eigenvalue and 2 eigenvector that we're going to denote. So the detail of that, it's in the tutorial. So you have 2 eigenvector associated with the 0 and 1 eigenvalue, and you're going to see that the action of this C dagger and C, so the annihilation and creation operator, so this is what I'm going to use. And so you see that here, in a way, things are simpler because you're going to deal with a 2-dimensional Hilbert space. And so, of course, to go to the path integral formalism is going to look really complicated just to deal with kind of 2x2 matrices, okay? But I think it's a good example to see how things work. So I'm not going to do a more complicated example here. Okay, so now we can, of course, work in this Hilbert space just spanned by these 2 vectors. Okay. So now this means that any arbitrary vector in this Hilbert space is just written like where f0 and f1 right now are just complex numbers. So right now we don't have any Grassmann number. But let's now introduce some other state that we are going to use to represent our unitary time evolution operator, okay? So let's now introduce this, so I'm going to introduce theta defined as, and the dual one okay, and we're here now and why these states are interesting. So they are called current state, but not really what we're interested there. It's if you look now at the action of C and C dagger respectively on this state, you will see that they are eigenvector. Okay, so C on 0 is 0, and C on 1 is 0. Okay, so what do we get? We get that this is equal to, so let's keep the same order. So how do you see that it's, I've just told you that it was an eigenvector. So this equality doesn't show you that. So how do you show that it's indeed an eigenvector?
Multiply by theta.
Or by theta. If I multiply by theta, I'm going, so this is going to vanish, but I can say that I'm going to tell you that this is the same thing as.
Sure.
Agree? Okay, good. So now I proved just what I just said. Okay, this is an eigenvector. Now let's do something quite similar on this one. And here we just use, yeah, so C dagger. So here, what do we get? But again, we use the same trick, okay? And say that it is not really a trick. And in fact, we're going to see that we use this kind of thing very often, okay? So just because you can, when using the fact that a Grassmann number squared is equal to 0, then sometimes you have some equality where you have an exponential is equal to just a number. So you really have to figure out, yeah, expand everything and check that indeed most of the terms are vanishing. Okay, so just one, before going to the path integral, one important relation that I need. So I just want to compute the scalar product between two theta vector. So what do I get here? I just expand, okay? One times the 0. And so 0 with 0 is 1, and then 1 with 1 is 1. All the other are 0. So what do I get? I just get 1. Okay, and so of course we're going to use that because we're going to compute now the so what is the object that we are mostly interested with. To go to the path integral formalism is going to be the matrix element of the time evolution operator, and we're going to use this representation. Okay, so any question on that? Yeah.
One question. So when you're writing the definition of C and C dagger,
Yeah.
C dagger x on 1, and does it give the 0 vector or the 0 number?
Zero number.
Yeah, the 0 number, sorry. Yeah.
Yeah, okay.
Yeah, so thanks. Yeah, you're right. So here.
Zero vector, not zero cat.
Yeah.
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 No. The other.
Sorry, yeah. Oh, sorry. So, yeah.
C dagger.
Yeah.
Vector on 1.
What?
In the middle of those two. See dagger acting on one.
Oh, yeah. Now, okay. C1 is, okay, thanks.
Yeah.
Here. Sorry about that. Okay, thanks. So is it correct now? Because yeah. Okay. Yeah, perfect. Thanks. Sorry for the confusion. Okay, so but Okay, so now let's move to path integral. And we keep the one state problem, okay? And so to make the parallel with the bosonic case, so we started with, what was the starting point? Okay, the starting point was to write, was the time evolution operator that sometimes you go, and we did the weak rotation. So also here we're going to just work with imaginary time, okay? And then we were interested in this kind of object, okay? So the starting point for the bosonic case was to look at this kind of okay, meaning that here we were using the position representation, okay? So we're looking at the matrix element of the time evolution operator recoded in the position representation. So in fact, if you really want to make the parallel with the representation we are going to use here, we should go, there is, and I think I'm going to ask you one question in the homework too about that, to go to this more holomorphic representation, so to make the parallel. With what we are doing now in the bosonic case would be to go to the representation, where here then you're going to deal with analytic function, so per-integrable analytic function of some complex variables, and of course you remember that, so x, the operator x, we have seen that we can write it in terms of a dagger a, okay? So you really start with the main object are going to be your a dagger a, that of course are satisfying some now commutation, anti-commutation relation, and not anti-commutation relation. And then you would work with kind of eigenvector for this a and a dagger. And this formalism is going to be also the starting point of the second quantization formalism that you're going to see tomorrow, okay? Where it's quite useful, in fact, when you want to generate to the case of n-body system, okay? So here, when we're dealing with only one x or one p, it's totally fine to work in the x representation, but if we want to generalize that to many-body system, it's much more convenient to work the path integral formalism using this kind of second quantization tools, meaning this a dagger. And it's really also from this point of view that you can really see the parallel with what the with the basis we have been choosing here in for the fermionic case. Okay. But so now to do the path integral, just maybe before starting. So this is the starting point. Okay. So we want to generalize this, except that now we are not working in the position representation, but we are going to work in this using this basis. Okay. And I'm going to do. So we want to do the same step here. To simplify a bit the calculation, I'm just going to consider this operator, this Hamiltonian. So it's exactly the same up to a constant. Okay, here if you use a commutation relation, you're going to find that it's going to be omega of c dagger c minus 1/2 of omega, where omega is a complex number. Okay, it's just because why this is nice. So this now is a fermionic case. So why this is nice? So if you compute now h0 squared, what do you get? Okay, so it's going to be omega is just a complex number, so it can go. Then you have to be careful with the order. But so what can you say? So now if you swap these two, it's going to be 1 minus c dagger c So then you get C dagger C minus something in C dagger CC. Okay. So you see that this second term is vanishing. So you're only left with omega squared C dagger C, which is omega times H0. So now let's work on, so before looking at the matrix element of this operator, let's look at the operator itself. So we define, again, we're using kind of imaginary time. I'm still using the letter T, but it's minus H0. So we use this object now. So let's try to rewrite this in a nicer way. So I'm going to expand it. Okay, so it just, so this is an operator. So I got minus, and then I'm going to use the fact that H0 squared is going to be omega H0. Then okay, so you can see that in fact this, if you now factorize by H0 here and omega, what do you get? You're able to rewrite this in fact as, so there is this first term, so we keep it plus, and now it's, in fact you get an exponential of minus omega t times just H0 and everything divided by omega. Okay, so this is just rewriting this expansion here. So what is nice, of course, is that it's, again, just linear in H0. So now we are able to, we have this operator. So now let's look at the matrix element. And I'm going to use these bases. Okay, so here is just identity. And so I'm just going to get the, theta prime. And then, so this is just some real number. So I just, this can go out. And then I need to find the matrix element of H0. Okay, so H0 is just omega, so the omega is going to cancel, and then it's a C dagger C, so I can just use what we just proved here, okay? So what is going to come out is that this is just equal to omega times, so I have, and then the C is going to act on the theta prime here, and I'm going to get the vector theta prime times theta prime. Okay, so then we just computed that here. Okay, so you see that this is just 1 plus this number, and here, in fact, you're going to get, so how this is going to simplify? What do you get here? Yeah, so just be careful because here I wrote it the other way around. Okay, the prime was on the other side, but anyway, it's not going to change this result because the only term that is going to contribute, so if you write this is 1 plus something, which is in terms of theta and theta prime.
That's gonna vanish.
Yeah, okay, so only the 1 is staying, okay? So you just keep this number here. So now if I rewrite everything, what do I have? I have 1 coming from here plus So from this first scalar product, plus, so the omega is going to cancel this one, minus 1 times. Okay, and so now these two terms are vanishing, so I'm just left with 1 plus epsilon and again this can be written as compact under the compact form. This is just here, so here this is still the result. You can use that, of course, to make explicit calculation, but you can also rewrite this as just the exponential of okay, any question? Okay, so then what was the second step? No question? Fine. So then what was the second step? When, so I told you we started from the propagator. So this is the propagator. Now we have the matrix element of the time evolution operator to go to the path integral representation. What did we do?
The J,
Sorry?
we have to add the source somewhere.
So no, not yet, because the source was when acting on already when we already had the path representation. Okay, so here we're starting from the propagator, writing. So you remember we were so really starting from this object, and then to show that this object indeed was indeed equal to something like this of exponential minus s of e, where here you have the path condition but you remember that this is a kind of can you read? This expression is a kind of formal expression, okay, which we're hiding the fact that this should be written as a limit when n goes to infinity of something we wrote here. So to get to this expression with this limit, do you remember what we did? The idea was, so here we have a finite time interval. Okay, so here it's just t. I'm considering I'm going from 0 to t. And the idea was to divide this time interval in n subinterval. Okay, so we're going to do the same thing here. But do you remember, so in this case, why was that possible to indeed say that was indeed equal to so this was a question, I think, in the homework 1. Why can you write this? Okay, and here it's because h is time independent, so it's commuting. Okay, otherwise you have a so you should check. There is a I don't know. Last time in the tutorial, someone wrote the name of. I think it's Sarah. Right? Oh, he wrote the name of you know this formula with
Baker Campbell.
Yeah. Thanks. Okay, so if it's not commuting, then you have additional term, and the formula is given by this. Okay, so here we first need. This is what we want to do. Okay, to divide our time interval, but we need to check that indeed we can write. So let's say that this. So we're really doing more or less the same step. Okay. Then calculations are going to be easier because more or less everything is kind of linear function. So it's like very simple. So here we need to check that indeed we want to divide our time interval. So here it's just t into n subinterval of duration time t divided by n. So what we need to check before doing that, okay, we need to check that indeed if that u0 of t indeed can be written as u0 of and so I'm not going to do it really, but what you can check, I let you do that explicitly. It's very simple. You don't have to do for n, okay? What you just need to check is that indeed, if you look at, for example, something like this, t prime, this is indeed and this is easy to check just using the definition you have here. Just using this expression, okay? So just the definition of, in terms of h of u0 here, and the fact, of course, that h0 is equal to h0 squared is equal to h0, okay? And so you just need to expand everything, and everything is going to cancel nicely. So this is fine. We can do that. And so then what did we do here? So here we did the same thing, okay? We wrote before arriving here in this bosonic case. So we were also able to say that this object could be written just as a product of u, where now with the time duration was something like epsilon, and we had n of them. Okay, so we had a product like this of u, but do you remember what we did then to arrive to? So here we just have this scalar product. We have an operator acting on x prime, and now this operator can be written as a product of several operators. So what did we do? Yeah, okay. Between each of these u, you remember, we introduce a resolution of identity. Okay, so here we need the resolution of the identity first. So this is what we're going to introduce here, but let's first maybe introduce a resolution of identity. And I'm telling you that we can consider this completeness relation where we use and I'm telling you that this is equal to identity. Okay? So since I think it's maybe good to, so this calculation is quick and it's going to remind you a few things on integration. So let's do it together quickly. So this, I'm just going to use the definition, the explicit definition of my ket theta in terms of 0, 1, and my Grassmann number. Okay. So and then I'm going to say that, of course, this is the exponential, but only the it's just linear, in fact. only this term contribute. So now, if we just expand everything, and then we are going to need to remember. So here you have two integration with respect to two variables. So you need to recall that. What does it mean? What is the order you're going to use? But let's write which term as. So in fact, here we're going to. This is going to give us a derivation. So the first derivation is going to be with respect to theta. And the second one with theta star, okay? So here, we need to keep only the term in that have at the same time a theta star and a theta, okay? And this can, anyway, you cannot have a bigger term, okay? Because it's going to anyway vanish, higher order term, I mean. So the only term left here is going to be, so you have the 1. So I'm keeping only the term of interest, okay? So it's this one with this one and the one here. Then the other one is going to vanish because you will have theta squared. Then this one is going to be, when you take the derivative, you're not going to see it anymore. So we don't care. And then, but we have the 0, 0 with this minus theta. So we also have and then plus some constant term, okay? Constant term with respect to theta. So now we take the derivative, so you have to be careful, remember the order. So here it gives you a 1, the 1, 1. And here, what do you get? The first term gives you so do you get this or plus, okay? Because you need to act first with this derivative. It's anti-commuting with theta star, so then you get the minus, the sign you want. Good, so this tells you that indeed this is identity. Perfect. So now we have everything we need to write quickly what is the path integral. And then, but it's not going to be very long, in fact. Especially that, so we are interested in this u 0 of t divided by n, okay, and then to take the limit n goes to infinity. So we are only interested in u of 0 for very small t. So what we're going to do is, in fact, look at the first order in t of this operator. So then everything is really like linear, so it's going to be. So before introducing this resolution of identity between each step, what I just want to do is, since we are interested in the limit n goes to, this means that the interval t over n goes to 0. Okay, so we can look at the time evolution, the matrix element of the time evolution operator at the first order in t. So then I'm just using this expression here, okay? So I have 1 plus time the exponential of minus omega t, but this I now expand that as and this of course can be also written as the exponential of Okay, so now what we're doing is really do the same thing as before, meaning I'm going to write, so let's consider this object now. And then I'm going to take the limit when n goes to 0, infinity. And I'm going to introduce many so identity resolution that I just introduced. Where here, what we're going to consider is U0 of and then we have a resolution. So the resolution is with, sorry. So I need I'm interested in matrix element. Okay, so to see how things work, let's just do one. Yeah, it's going to be easier this way. Sorry, so I'm going to take the limit at the end. I'm just going to introduce one identity resolution, and I'm just going to consider that I'm going one division of my time interval. Okay, so I'm going to just say that this is U of t to U of 0 t divided by 2. And so I'm just rewriting that. I'm introducing the identity resolution between the two here. Okay, so let's just do that this way. Otherwise, it's going to be really too messy. Okay, so then I have something like this. And U0. And each of these terms is very simple. It's something like this. Okay, so here what I get so I just get something like 1 plus times theta times 1 minus omega t. So this is for this first term. Okay. Then I have my exponential. So here I can commute these two. Okay, because yeah, there is two of them, so it's not changing the sign. Okay, so you can commute these two. So here you can write that this is 1 minus. Okay, so just to make clear, this term gives this first bracket. Then this exponential gives this second one. And then the third bracket is just the evaluation of this one. So you get 1 plus theta star theta prime times 1 minus omega t, which come from this last term. Okay, and so if you just rewrite everything, you can really write that this is it's a 1, which is going plus some linear term in this product like this. So you're really going to be able to write this as an exponential. Okay, plus, so I'm just rewriting, adding this term that is going to vanish. It's just because I want to make appear some difference. Okay, so here I just really reordered all these terms, remembering that yeah, there is no quadratic term in any of these variables, minus omega epsilon, where here epsilon is t over 2, but it's going to be, if you generalize this, it's going to become t over n. Okay, if you do that for many intervals. And then you get this okay, so what can you say about that now? So if now I generalize this, okay, if I consider that, so this is my final point, the prime, okay? The prime is my initial point, and you see that here I have only one intermediate state, which is this theta, one intermediate position, if you want, which is this theta. So you see that you start from the final point, it's the intermediate position minus the final, then the final, the initial position minus. So it you get a kind of pattern that you can generalize with if you introduce many identity resolution between each of your u of t divided by n. Okay, if now you consider really n subinterval. So at the end, what you get, so this is just when n is equal to 2, but now if we get the general case, just end up with something of this form, which is really the equivalent of the limit expression we add to define the path integral in terms of a limit. And then we can, as for the bosonic case, we can give a kind of continuous interpretation. So now I introduce n-1 resolution of identity. And you see that here I expanded that, but this can really be seen as the exponential of all these terms, okay? Because it's 1 plus this linear term. So here I'm going to write this as an exponential. And what do I get? I guess it's a so this is just okay, so it's really just a generalization of what we wrote before with the kind of notion of discrete action as we had in the bosonic case, where here, let me define. So again, now epsilon is t divided by n. This theta n or theta n is theta prime prime. It's my final point, and my kind of generalized discrete action is exactly what was written here, except that now you have a sum over k. And omega epsilon and so this is would be, if we want to start doing some concrete calculation, is going to be the expression you need to use. As we in the bosonic case, we started with defining what was the representation in terms of path integral of this object. We ended up with a limit, and then we had to use this expression in terms of a limit, for example, to compute explicitly what was the propagator, the path integral representation of the propagator for the free particle. So here you should do the same. Then, of course, there are also equivalent approach that was developed in the bosonic case that can be generalized to this case. But so let's maybe just, as in the bosonic case, we can write a kind of formal expression taking the, so if we take the formal limit where you get a kind of generalized path integral with what we could call Grassmann path. Okay, so the path here, the variable here are Grassmann variable, so you get something of this form. It looks, and really again, if you really want to have the connection between, or really a parallel between the bosonic case and this fermionic case, it's the parallel is much better thing if you work in the holomorphic formalism in terms of the representation for this creation and annihilation operator using this. So here I'm going also to define this formal. And now we can define this the kind of equivalent to this kinematical term where a kind of action will be defined with, I'm just finishing, S0 is an integral from 0 to t here with a from dt, where we define the derivative. Taking the limit against this term, if we divide by epsilon, okay, we can factorize by epsilon, divide by epsilon. This term looks like a velocity term, okay, a derivative term. And the last term is just omega. Of course, I guess you cannot read now. So yeah, the last term is just omega theta of t. Okay? So this is the equivalent to, let's say, the first step that we did in the bosonic case. Then many of the tools that we, at least in the, some tools can be generalized, okay? But again, so everything we have done is for one state system. I'm going to conclude here. And the next step would be to generalize everything to allow n particle states. And I think this is what you're going to do, at least in the canonical framework. So not talking at all about the path integral framework, but tomorrow with Aggie, you're going to start talking about the second quantization formalism, okay, which is used to deal with n-state system. So thanks.